Hello and welcome to my presentation. My name is Alex Thatcher and I am a reservoir engineer for Oilfield Production Consultants, OPC. This study was done on behalf of our client, Nefin Energy, and the title of our paper is Dynamic Reservoir Analysis of Corrib Field Surveillance Data through the use of advanced deconvolution techniques. The business objectives set out by our client, Nefin Energy, were as follows. Determine hydrocarbon volumes and average pressure connected to the well stock. Maximize the use of associated investment in surveillance data. Use state-of-the-art technology to support commercial and technical considerations. The technical objectives of our paper are as follows. Present alternative techniques for determination of in-place volumes and average pressure. Show that pressure rate deconvolution can be used on long-term surveillance data. And finally, prove that single well deconvolution can also work in fields with multiple connected wells using drainage area theory. Corrib is a dry gas reservoir. It is Ireland's only producing field. It is a subsea development with 6 vertical wells. It has complex geometry, low permeability, and is heavily faulted, particularly to the southeast of the field around well P2. Keep this in mind, as P2 is our case study well for today's presentation. The GIP from static/volumetric interpretation is 1.2 trillion standard cubic feet. The field came online in late 2015, so we are dealing with 6 years of production data. Corrib is a joint venture between Nefin Energy, Equinor and Vermilion Energy, who are the operator. On the data plot, we show initial indications of interwell reservoir connectivity during field startup as the wells were brought online sequentially over a period of 8 months. We clearly see signs of pressure communication as some wells produce while others remain closed observing field pressure. Especially our case study well P2 shown in pink. During this time period, P2 is closed monitoring pressure signals arriving from the other producing Corrib wells. This proved that pressure communication between Corrib wells exists, and thus any analysis on this field would require a multi-well approach. However, after reviewing the 6 years worth of Corrib field dynamic behavior, it was surprisingly concluded that this field data can be analyzed using single well pressure rate deconvolution applied to the data of each reservoir well separately. The 6 wells had dynamically divided the reservoir into separate drainage areas and the well interference in a way disappeared. The wells behave as if each of them produced from its own drainage compartment. It is this condition that allowed analysis on a single well basis instead of a multi-well approach, and we will demonstrate this today using case study well P2. P2 is located towards the southeast of the field, where it is heavily faulted as shown on the structure map earlier. We are dealing with 6 years of pressure and rate data. The downhole pressure and temperature gauge is located 1,000 feet above the perforations. The well rate is recorded by an individual subsea flow meter. An annual field shut-in for maintenance for around 5 days occurs every September, and during this PBU the well is shut in at the wellhead. Permeability is estimated at 8 millidarcies. If we zoom in on the September 2020 PBU, we see a steep rise in pressure behavior that never stabilizes to an average pressure. Overlaying the annual pressure buildups from 2016 to 2020 on a Bourdais derivative plot normalized by rate shows remarkable consistency between all these transient pressure behaviors throughout the years. This indicates no change in reservoir properties. This information provides an initial indication of the linearity of the system, which is a key requirement for pressure rate deconvolution. The dynamic reservoir analysis approach is based on a form of pressure rate deconvolution. Pressure rate deconvolution is a method for converting the pressure and rate data obtained from a well operating under variable rate conditions into a much simpler form of constant rate drawdown pressure response function from the same well. The constant rate drawdown response function presents itself as a Bordet derivative that spans the entire test time, in our case 6 years. Pressure rate deconvolution can only be used with the well data that are consistent with the principle of superposition. In our case of gas reservoir, gas properties depend on pressure, and this makes the problem of fluid flow in the reservoir nonlinear and inconsistent with superposition. However, we apply pseudo-pressure and material balance pseudo-time transform to the well pressure and rate data. These transforms linearize the flow problem and make it consistent with superposition. This is extensively explained by Levitan and Wilson in SPE 134261. The deconvolution approach utilized is a manual method, not automatic pressure rate deconvolution that most people are familiar with. Automatic deconvolution relies on mathematical algorithms and regression techniques which are not robust enough to be used with data sets acquired during long-term production operations. For Corrib, we use specialized software which manually adjusts the drawdown response function so that the results of convolution match observed pressure data. This form of deconvolution was first presented in an earlier paper, SPE 195441 for Tamar field Israel. We now perform this on Corrib well P2. Here we complete a basic demonstration of the deconvolution method on Corrib well P2. I present the pressure and rate data of well P2. In green is the measured rate data, and in blue is the pressure measurements recorded from the downhole gauge. When we apply pressure rate deconvolution, we came up with this response function shown. This is the single well convolution equation. Pi is initial pressure, Q is the measured rate data, and Pu. This is the unit rate pressure response function, or response function for short. This is the unit rate response function, and this is the derivative of the unit rate response function. In our approach, the shape of the response function is adjusted using specialized software so that the results of convolution of the response function with well rates sufficiently match the downhole pressure gauge. Well, what does this mean? Well, by feeding this response function through the equation and solving for PT with the measured rate data gave us this result in red on the data plot. Now, when reconstructing this response function, the late time pressure response required a unit slope, meaning we are now out of transient behavior and in the world of material balance. In other words, the flow regime is in pseudo-steady state. This unit slope is translated into a gas initially in place within the drainage compartment of well P2. And this deconvolved curve also reports average pressure within the drainage compartment over time. Now, these were surprising results, since interference tests during field startup clearly showed well interference between Corrib wells, and therefore we would have to use complicated multi-well deconvolution. However, we clearly have an excellent match on 40,000 hours of pressure data using single well deconvolution. Therefore, we concluded that multi-well deconvolution was not required due to reservoir architecture, geology, and offtake strategy of Corrib, allowing P2 to establish its own stationary drainage area. Using this deconvolution approach over a sequence of PBUs quickly gave us precise insights into well JIP, average pressure, and character of drainage area. Here I present a real-time example of completing manual pressure rate deconvolution on P2. Here is the specialized software panel. On the left is some analysis data. In the middle is the response function pane. In blue is the September 2020 PBU. This is shown here as an initial indication of what the response function looks like in the first 100 hours from the well. We use it as a guide when reconstructing the response function. On the right is the gas rate shown in green, historical pressure data from the downhole gauge shown in blue, In red is the result of convolution of the response function, and in green is the average pressure. Now remember, the objective here is to interactively iterate on the response function so that pressure computations sufficiently match the historical pressure data. So using the software, I will manually adjust this parameter and continuously solve for this parameter, and the feedback will be shown here. And we keep doing this until the computations of convolved pressure match the blue data from the historical pressure data gauge. When I start the video, please keep your eyes on both the response function pane and the data plot together. So let's begin. So here we use these green circles, which we call control points, which allow us to adjust the response function. And here we guide our response function over the first 100 hours of PBU data. And you can see quite clearly straight away we have a much better match. We add a unit slope in late time. This now means we're in the world of material balance and pseudo-steady state for this well. However, we still have too much pore volume, so we start to reduce this very accurately using the pane here. We can see a shift in my blue curve, and this is due to the material balance pseudo-time transform accounting for variation in gas properties. So we have to quickly readjust our response function, and then we have some work to do on this area of the response function. And now you can see we have a sufficiently matched computation from this response function, which overlays almost perfectly the historical data from the gauge. With a few more small adjustments, we would be able to get a match that lies exactly on the downhole pressures, and we have computed average pressure within the drainage compartment of well P2. On this slide, I would like to compare this analysis approach of using a sequence of PBUs and deconvolution versus a more traditional approach where pressures are extrapolated from single PBUs. One such technique is P star. P star is the pressure from extrapolation of infinite acting radial flow regime to infinite shut-in time on a superposition plot as shown. These pressure points are placed on a gas material balance plot P over Z versus P2 well production. Fitting a straight line through these points to P over Z equal to 0 should yield the GIP. Using this technique, the GIP would be 102 billion standard cubic feet. However, using the average pressure from deconvolution on P over Z plot clearly yields a straight line through all the points and indicates a GIP over 50% greater from P star technique. After performing pressure rate deconvolution on all Corrib wells, we overlay the 6 response functions to gather field-wide reservoir insights. The vertical separation between these lines clearly shows a field-wide reservoir property and geometry variation. In addition, we find that the wells with lowest productivity, i.e. highest vertically on this plot, also have the smallest connected volumes, whereas the best productive wells have the largest connected volumes, and this is due to drainage area theory, which is extensively explained in the paper. We also observed that each well has developed its own unit slope, meaning the limits of the Corrib reservoir has been collectively sensed by the 6 wells and are all in pseudo-steady state. If we sum up the dynamic GIP within each drainage compartment, we can determine the dynamic GIP of the field connected to the well stock, in this case 1.1 trillion standard cubic feet. Here we plot the average pressure from deconvolution for the 6 Corrib wells at the datum point. We clearly see that several pressure regimes exist across the field and that we are depleting the north of the field, well P3 in green and well P6 in black, faster than the rest of the field. Using this analysis workflow, the Corrib-related findings were as follows. The wells have dynamically divided the reservoir into separate stationary drainage areas. Several pressure regimes exist across the field. Overlay of the well response functions show Corrib is heterogeneous. The dynamic JIP connected to the well stock is 1.1 trillion standard cubic feet, which is reasonably in line with volumetric static JIP of 1.2 trillion standard cubic feet. In terms of the analysis techniques, the paper will be valuable to the industry as it demonstrates the following. P over Z technique using individual PBU is not sufficiently accurate and consistent in many cases. Using a sequence of PBUs and pressure rate deconvolution can be far more accurate in determining average pressures and connected volumes to the well stock. Comparing deconvolved response functions on a Bourdais derivative plot provide deep insights into reservoir characteristics across a field as a whole. Manual pressure rate deconvolution technique is robust and reliable enough to handle real surveillance data and gives confidence to the user. Not every multi-well situation with proven interference requires complicated multi-well deconvolution. The paper presents theoretical foundation on drainage area theory using synthetic examples for those who are interested. Thank you for listening to our presentation, and we hope you enjoyed it. The authors wish to thank the Corrib joint venture partners, Vermilion Energy, Nefin Energy, and Equinor for their support and the permission to publish this paper. We also wish to thank Dr. Michael Levitan, the author of the methodology and the Convolution Explorer software that facilitates the manual pressure rate deconvolution technique used. We also thank him for his technical advice, guidance, and the support in preparing this paper. Thank you.